Next, let's talk about one of the most important um, concept in the networking layer, which is IP addressing. So although most of you are familiar with IP addressing at some level, it's very important to have an understanding of it and how it works. So basically you have a IP network with different subnets here connected to 3 different ports on a router as an example. So basically an IP address is a 32-bit identifier, unique identifier um, for a host or router interface. And we say interface because obviously not only does a router have multiple interfaces, but even a host these days will have multiple interfaces. You usually have you can have at a minimum, most hosts have a wireless and a wired interface, each of which will have a different IP address. So an interface basically, of course, is the connection between the host and or router and a physical link. Like I said, routers typically have multiple interfaces, although most hosts do as well. Like I said, a host typically has 1 or 2, usually 2 these days, wired Ethernet as well as wired 802.11. And here we have an example of an IP address, so you can see it's a decimal dot notation. So you can see this is 223.1.1.1, which is represented in this particular format. Basically, IP addresses are on the network are divided up into subnets. So a subnet is basically a little network where communication can occur without the use of a router. So we have here these hosts, and this is the subnet. So this is a 223.1.1 network. So any hosts that have 223.1.1, in this case we have 1 through 4. So we have these 3 hosts and the router port. So this is one particular subnet. So these hosts can communicate to each other without having to go through the router. You have another subnet here, which is the 223.1.2 network. So every host in this network starts off with an IP address of 223.1.2. So you have .1, .9, and .2 in this particular example. And down here you have the 223.1.3 network. And we have the subnet mask, which we're going to talk about very shortly, of /24. So all hosts on a subnetwork have the same prefix. The portion of the prefix is indicated by a subnet mask. So basically, in this example, the subnet mask is the first 23 bits. So that means the first 23 bits are going to be the same for every host on this particular network. That's why we have this the subnet mask here. So basically, this is basically the subnet that we're on from this point. So there's different types of IP addressing. The older kind, which is what we used to call the classful addressing, and the more modern classless IP addressing. There's 2 different ways of subnetting IP addresses. So in the older classful network, we basically divided the IP address space into 4 classes of network. in the first bit in class was a class A, class B, class C, and class D. And so in the class A network, always had the first bit was 0. The next 7 bits were the network subnet, and then you had 24 bits for your local IP addresses. Below that, you had class B networks, which always had the first 2 bits of 1, 0. The next 14 bits were network subnet, followed by 16 bits of local class B addressing. This was followed by the class C network, which had a 21 bits. We always started with 110, and next 21 bits define the network address, and then you had a very small local 8 bits for local addresses. So basically, the larger an organization was, the more address space the organization needed. It basically got a higher class network. And then finally you had class D, which was used for multicast. But what happened is, using this type of structure, we were basically running out of addresses very quickly. So we went to the classless IP addressing scheme, also known as CIDR. So in CIDR, we have a lot more flexibility in how we set up our subnets. So basically, rather than be fixed length like in the class full system, the subnet portions of the address is basically an arbitrary length. And basically, we identify the address format by using the dot decimal notation and with a /x, where x is the number of bits in the subnet portion of the address. So in this case, we have defined that our subnet portion is going to be 23 bits. So if we count, this should add up to 23. And then we say that we define it as 200.23.16 as our subnet, and the other bits are basically the host address space. So how does a host get an IP address? So there's basically 2 different ways. Either the IP address is hard-coded. This is how you would hard-code it in Windows. This is how you would hard-code it in Unix. So there are certain networks that don't use, for whatever reason, don't use DHCP, but rather have a hard-coded IP address scheme, and usually those systems are run by sort of system administrator. However, today most IP addresses are assigned dynamically by using a DHCP, which I'm sure most of you are familiar with. And DHCP, of course, stands for Dynamic Host Configuration Protocol. So we're going to talk a little bit about the mechanisms of DHCP. So the goal in DHCP, rather than having static IP addresses that have to be configured, we want to be able to dynamically have an IP address be assigned to a particular host. So DHCP server has some IP addresses that can be used, and it basically dynamically assigns those IP addresses to hosts on the network that communicate with the server. So what are some of the things that the DHCP server can do? It basically can renew, a host can renew its lease on an address in use. So it can keep, basically a host can have an IP address for some time period, and it can basically say that it wants to keep that particular IP address on on a updated period after the lease has expired. Um, it allows the reuse of addresses. So if you have a lot of hosts, but not a lot of hosts that are, you don't have all of them on all the time, you can have a potentially a smaller number of IP addresses than hosts, and you can basically kind of reuse addresses. Um, it also provides support for mobile users who want to join the network. And since mobile user ad hoc, DHCP works very well for an ad hoc configuration. So basically the way DHCP works is 4 steps, 2 of which are optional. A host can broadcast a DHCP discover saying, hey, I want to find out what's out there, and a server will respond with an offer. We're going to talk a little bit more what that means. Or the host can ask for a request for an IP address and for a particular server, and then the server respond will send the address with an acknowledgement that it received the message and send an address to the particular host. So let's take a look at the mechanisms of what causes this to work. So imagine you have an existing network and you have a client that needs to be connected, in this case, to this particular network over here, this 223.1.2 network. This is basically the handshaking that will occur. So basically the client sent the broadcast out on the network looking for a DHCP server. The DHCP server gets the broadcast message. It says, I'm a DHCP server, excuse me. Here's an IP address that you can use. And then the client will return and say, okay, I'll take that IP address. And then the DHCP server will provide an acknowledgement that yes, that client will be officially assigned that address. So there are other things that DHCP does besides provide IP addresses. So when you connect to a DHCP server, you can get additional information. For example, you can get your default gateway, which is the address of the first hop router that each of the clients on a subnet are going to use. So this basically provides dynamically a lot of the other configuration parameters that a system administrator would normally configure on a host. Additionally, the DHCP server can provide the name and the address of a domain, the domain name system server, so the host can do address resolution, and also a subnet mask, so the host knows which subnet it's on, so it knows when it needs to talk to somebody locally or when it needs to send traffic and point it to its default gateway. So let's take a look at an example of how DHCP provides all this data to a client. So you have a situation where a connecting laptop wants to join the network. Not only does it need the IP address, but if it needs to communicate, outside the local network, it needs the address of the first hop router and the address of the DNS server if it's going to resolve any host names. So the DHCP request is encapsulated in UDP, and then in IP, and then in 802.1 Ethernet. The Ethernet frame with the destination of all Fs, basically the broadcast frame, is sent out and it is received at the router that's running the DHCP server. Then the Ethernet is demultiplexed to IP, demultiplexed to UDP, and finally demultiplexed to DHCP. The server then formulates a DHCP ACK containing the client's IP address, the IP address of the first hop router for the client, the name and the IP address of the DNS server. The encapsulation of the DHCP server frame forward to the client is demultiplexed up to DHCP at the client. Now the client knows its IP address, the name and the address of the domain name server, and the IP address of the first hop router. Next, let's take a look at network address translation. Sometimes an organization uses what is called private addresses. These are IP addresses that any organization can use inside their network. The good thing about this is that it gives organizations the ability to not waste the public IP addresses, and it gives a chance for these private addresses to be reused over and over and over again. So this really it really helped the IPv4 IP address scheme to last a lot longer than was expected. The only thing about these private addresses is that they are not routable. They cannot go onto the internet. So because of this, we need to do something called network address translation. So imagine you have a local network, maybe your home network, or maybe a network at a small business, using these private IP addresses. And you need to communicate to the rest of the internet. So what happens is your connection, your router connection to the outside world is assigned what's called a network address translation, or NAT, IP address. So all your datagrams leaving your local network will have the same single source NAT IP address. In this example, it's 138.76.29.7. So what is the reason that we use network address translation? Well, this really helps out, once again, with the efficiency of the use of IP addresses. Now a local network can use just one IP address as far as the outside world is concerned. You probably have this on your home network when you have multiple devices at home, but your internet service provider only provides one IP address to the rest of the world. Now this way, a range of addresses is not needed from your ISP, not needed from your ISP. Just one IP address for all of your devices. And this allows you to change the addresses of the devices in your local network without having to notify the outside world. Likewise, it lets the ISP change its address. It allows you to change your ISP without changing your addresses inside your local network. Can you imagine a home user that changes their internet service provider having to go and reconfigure the local network? That just would not work. The other nice thing is it gives you a little bit of security, because devices inside your local network are not explicitly addressable or explicitly visible by the outside world. So How is network address translation implemented? So in order for network address translation to work, a router set up as a network address translation router or NAT router needs to do the following. So when it receives outgoing datagrams, it has to replace the source IP address and port number of every outgoing datagram to a NAT IP address and a new port number. The remote clients and servers will respond using the NAT IP address and new port number as a destination address. So when it's making this change, it has to keep track of the translations that it made. So therefore, a NAT router needs to maintain a translation table. That translation table has to have an entry for every source IP address and port number and every NAT IP address and new port number translation pair. Likewise, when an incoming datagram comes in, it needs to replace the NAT IP address, new port number, and the destination field of every incoming datagram with the source IP address, port number stored in its NAT table, and then send that on to the local host. So here we have a graphical example. So here we have a bunch of hosts. On our local network, we have a 10.0.0 network, and we have host 10.0.0.10.0.0.1 through 10.0.0.3. And this particular host here sends a datagram outside of the local network to the internet to a host with an IP address of 128.119.40.86 on port 80. So basically it's making a HTTP connection. So it sends the datagram out with this as a source address, this is a destination address. The NAT router then changes the datagram source address from its original value to a new value with the IP address corresponding to the assigned IP address, and it gives it a new port number, and it saves it in its translation table. So that message gets sent out with this new source address information. Thus, the destination replies. It gets a reply back, and it's expected to go to 138.76.29.7. The router receives that message, looks up its address, its translation table, and then provides the new address that corresponds with the local network so the local host can receive the datagram. Okay, so NAT uses a 16-bit port number field. This allows up to 60,000 simultaneous connections with a single LAN site address. If for some reason you need more than 60,000, then you're going to have multiple IP addresses on the multiple NAT IP addresses. However, one of the issues with NAT is that routers are only supposed to process up to layer 3, and obviously that's not happening here. And that possibly can, so this violates the end-to-end argument. NAT possibly must be taken into account by application designers, such as peer-to-peer applications. And basically, NAT is basically a band-aid until we have full usage of the IPv6 address space. But nevertheless, it does tend to work, and it's used all over the place these days. So, in spite of those controversies, it works very well. So, Let's take a look at a NAT traversal problem. We have a client that wants to connect to a server with the address of 10.0.0.1. The server address, obviously, is local to the LAN, so the client can't use it as its destination address. It can only use the NATed address, which is 138.76.29.7. So one solution to this problem, if we have a server on our private network, is to statically configure NAT to forward incoming connection requests at a given port to a server. So if we know that the server takes connections on port 2500, we can, or 25,000, maybe 2500 to the outside world, we can do this, have a static configuration and always convert this address and port number here to the 10.0.0.1 port 25,000. A second possibility is to use universal plug and play. So let's step back a second and discuss what universal plug and play is. So with universal plug and play, NAT needs to be manually programmed to forward external requests. UPnP allows hosts to request port forwarding. Both the host and NAT should be UPnP aware, and that is usually true these days. Host requests forwarding all port XX messages to it. NAT returns the public address and the port number, and the host can then announce the address and the port number outside. This allows outside hosts to be able to reach the internal host. So let's go back to our traversal problem. In this case, we use universal plug and play internet gateway device protocol. This allows a NATed host to learn the public IP address and add or remove port mappings. Then automate static NAT port configuration. A third solution is called relaying, and this is what's used by the Skype application. In this case, the NATed client establishes a connection to some relay. The external client connects to the relay, and the relay bridges packets between the two connections. So in this case, we have a host behind the local network, and it wants to make a connection. So basically, it connects to a relay, and that connection is initiated by this NATed host. Then you have a connection to the relay that's also initiated by a client, and then the relay is established, and then the connection can be made between the local host and the internet client. And that's all we have for this lecture. We'll be continuing our second set of lectures in the next video.